Alright, so hey there guys, welcome to Circuit Shorts, and today I'll be discussing something random in my random vlogs. So let's just move this one here and let's get started. So we're gonna discuss about the caption project I've been making for over 2 semesters, of which only we got like 8 months to make. And it's not really a very complicated or sophisticated project. It's just a very simple design for actually Arduino based design. So the design considers the overall concept of different semiconductor components, and the basic objective of this project is to protect the induction motor, single phase load as for now, because our project wasn't that complex considering the budget and all. So the basic concept is that you use semiconductor devices to make a solid state switch, a zero voltage switching type, and the overall topic would be the protection and real-time monitoring of single-phase induction motors. Single-phase induction motors, because we needed to test some things out, and we didn't want to get deep down into the, you know, the disastrous fatalities if the system doesn't work, and we needed to pull up the CGPA and whatever stuffs, internal stuffs of the college, and we're not going to consider that. So let's get started, shall we? And putting it into the center, let's see. And I've designed this on the EasyDA simulator. So simulator is not the really thing. It should be actually the standard model. And well, let's see it in simulator because it is in simulator. So I don't really have anything big to show around here, just a little bit of overview of what our capstone project really was. So let's get started. I maybe said that quite a lot of times, but anyways, so the first thing I would like to focus on is the soft starting mechanism of our project. So our project is not very complicated work of art. It's just a very simple type of soft starter, I would say. And if I focus around here, then you can clearly see a delay circuit over here with some potentiometer and all, which makes sort of sense because considering the delay circuit is adjustable in overall scenario. So yeah, and these are the LEDs that would indicate that the soft starter is indeed working. So our capstone project with this soft starter was really a great success, but I would add the fact that it wasn't really a glorious novelty of a success. It was just, you know, we got lucky. So with this design, what we tried to do was that here comes the VCC, that is from the bench power supply, VCC and ground. If you can see the highlight points right here, and then it goes to a transistor. Now I don't know why my colleagues tried to add another opto-isolating transistor with another transistor, most probably for the sake of amplification and all. But yeah, anyway, he did a terrible thing with not adding anything else other than this simplistic circuit. Anyways, so the basic thing is we shouldn't have used this potentiometer here. We're just doing certain sort of shit. Anyway, so moving on, what happens here is the VCC. Let's say the switch is on. So right, so the transistor is active. So BD139 transistor is active, and then what happens is it goes to the first delay circuit right here. So the first delay circuit comprises of 1K resistor, 200 microfarad capacitor, and a MOSFET IRF-Z44. And because we couldn't find any other better MOSFET other than a power MOSFET, I don't know why. So Next is the activation, which goes to the LED. The positive rails go through, and there's a series of cascaded, I won't say cascaded, but an array of delay circuits, with each of them having their own delay set. Now, this is not a super complex circuit, and we try to keep things simpler for our sake and our team's sake, because, well, our team wasn't that good really. So anyway, so what happens is that the delay you have to set manually for the soft starting mechanism to occur, and the basic concept of this delay goes to here. So the basic thing is that this is a 220 ohm resistor, and this is basically a power resistor, a high voltage resistor. So it's around 50 watt, and here is a 70 ohm resistor, 50 watt. So the basic concept is that the array of these switches, the triac switches, goes through here. So when the first set of, let me show you around, the first set of delay circuit is turned on, then the highest resistor value of the triac, like highest equivalent series resistance thyristor, gets activated, and then the next lower resistance thyristor gets activated, and finally the final thyristor gets activated, shorting the entire circuit, and essentially making things a better for actually what happens is a bit of complementary commutation goes around. So since this one is active, the Q8 thyristor is active, or triac is active, so the Q7 and the Q1 thyristors are automatically turned off due to the forced commutation through the voltage shorting. So basically you can see through here that there is a certain voltage drop around here, and this voltage is nearly zero. So ignoring the voltage drop inside the thyristor, the voltage is zero. So what happens is the switch gets off, and that way the soft starting mechanism occurs, like you have a higher resistance, then a bit lower resistance, then you have a short circuit path. So that's quite a genuine method, but I wouldn't say it's a very splendid method or a quite you know quite versatile method. It's obviously useless as compared to PWM, but what we identified was the PWM has its own limitations on harmonics, which we didn't know that FACTS subject, like the flexible AC transmission system subject, existed back then, and we didn't know that about the inverters part, and we were basically doing the shit work of making a circuit in its hardcore form. So that was really useless thing what we did, and I wouldn't appreciate doing such a thing around. And I also don't know why we tried to have all these three LEDs over here. That doesn't really make any point. I'm just literally roasting myself right now for doing this shit fuckery. Anyways, moving on, what we do here is the measurement part over here. So this overall box, dotted box right here, stands as the ACS 712 as highlighted over here. And here comes the parallelly connected, the voltmeter type ZMPT101B. Now I will really like to discuss, I would really like to discuss about the drawbacks more than the features of this circuit. So the drawbacks of this circuit, features you know already. ACS 712 is for current measurement, be it AC or DC. It's like a Hall effect sensor, right? And the ZMPT101B is really dedicated to measuring the voltage levels and all. So these are the part of Arduino hobby kits and all, where you can just measure the voltage and work your way out. Other than that, the main drawback of our project, this is actually the legitimate circuit diagram of ZMPT101B. We did not find any sort of ZMPT101B IC or like a entire circuit board like LM2596. So we thought of making the entire circuit by ourselves, obviously by seeing through the circuit on our own. Other than that, the basic problem of the circuit, what we did where we messed up is that the voltage part. So there are two types of voltage measurement. The first one being RMS voltage measurement, which is a general RMS voltage measurement, and AC voltage measurement, of course, and the second one being the true RMS voltage measurement. Let me know in the comments below if you want to hear about me speaking on a bit on the voltage measurement part. However, the whole point is here that the voltage measurement and AC current measurement both went downhill. Because of that, we did not consider going through the AC voltage measurement through true RMS method. We just went through the normal voltage divided by 50 Hertz method, and we sort of did fuck up there, but whatever. And here is the Arduino Mega 2560. Why I don't know. I really don't know why we use this, because we could have just gone for ESP32 and worked our way through, but yeah, we did this. We went for Arduino Mega because we thought that it's bigger and better, bigger is better, the usual thing. And then what happened is we just increased the size of the project unnecessarily. We increased the budget of the project as well, which was really pointless. We could have just gone with ESP32 or ESP8266, which has higher processing speed than this one. Anyways, moving on, here is the display part, and it's nothing new, nothing much, because you have seen it already in Arduino forum and all. We just did some thing called copy, paste, and modify. Anyways, this is all about the LCD part. And anything I'm missing out on, yeah, it's DHT11, so it also comes with a temperature sensor. Not really a very cool thing. We can just get with a ESP32 to a temperature sensor. Never mind. So yeah, that's a temperature sensor. Does really nothing because DHT11 is shittier than DHT22, which is a bit better as compared to the voltage temperature range of sensing. And this motor could already go for just a class A insulation, because yeah, DHT11 can only read class A insulation temperature, and that too up to 80 degrees Celsius. I don't know how we thought about that. Anyways, other than that, what we used, the much I remember, we used NEMA MG Standards 1 for the most probably the design part, and there are a bunch of standards I would maybe mention in the comment section or in the description of the video if you want to know what standards, IEEE standards or IETE. What was that again? I'll write the standards in comment section down below. Yeah, IEC standards. So yeah, whatever. This is Circuit Shorts signing out. Adios.